everyone. Am I audible? Just someone can confirm. Okay. So, good evening, everyone, and welcome to the first of the 3 sessions in a webinar series organized by the joint collaboration of IEEE student branches of the 3 campuses of Pilani. For this series, we have handpicked these 3 domains, that is nanotechnology and algorithmic trading and computer systems, from the domain of science and technology, which we believe would be pretty useful and informative for our attendees. So for the first session, that is on nanotechnology, we have with us Dr. Vinay Sharma, a senior research and development engineer at Micron Technology, who has over 30 research articles published at the top tier journals, and he has also delivered talks at various conferences worldwide. So he has specifically chosen to introduce you all to the magnetic nanomaterials because of its great scope in medical sciences and engineering. Now, before handing over the spotlight to him, I would like to express my gratitude to him on the behalf of all the 3 student branches of Bitspilan for accepting our invitation in such a short notice. So, sir, over to you.
Okay. Hi, good evening, everyone, and thank you, Ayush, and I would like to thank Dr. Sandeep also for contacting me regarding this. So, yeah, a big thank you to the BITS Pilani team. So, okay, without any delay, I'll just start sharing my screen. You all can see my screen, right? Let me know if you can see the screen.
Yes, sir, it's visible.
Okay. Okay. So you can see now, right?
Yes, sir.
Okay. So you can see the title slide is the multifunctional magnetic materials, correct?
Okay.
Okay. Let me just check why I'm not able to see this. Okay. Okay, then I'll go ahead with the topic. So yeah, so the title for my presentation today is multifunctional magnetic nanomaterials. So yeah, first question before proceeding. So all of you are students, or is there any faculty also?
So we have invited faculties, triply faculties as well, but they're yet to join.
Okay, okay, because then my talk will be based on that agenda. So let's get started. So the outline is I'll be first speaking on magnetic nanomaterials for energy applications. So since I believe that most of you are from the nanotechnology branch or material science branch, so there are various applications where nanomaterials can be used in. They can be used from medical fields to the semicon field to the energy, etc., etc. So my title is mainly focused on the energy applications, and one reason behind this is because I did my PhD in the field of renewable energies. So I'll introduce you to briefly introduce to a concept called as magnetocaloric effect, MCE. Then I will talk about the development of low-cost materials and how do we make magnetic fluids from these magnetic bulk materials. And then once you get your materials, then how to design a device out of that. So I'll go through the proof of concept of this device. And then I'll also talk about some other some other multifunctional magnetic materials. So there is a long list of topics, but we'll see how much time we got. But if any one of you has some other doubts related to the nanotechnology or other things like what are the career prospects within this, and how should you choose your path forward, so you can ask anytime anything, because my presentation is a bit longer, but we can anytime divert from this. Okay. Yeah. So yeah, so when we decide on when we decide on doing research on particular topic of nanotechnology, then we first of all think about what's the problem statement. So for example, I just say here that currently what we are using are air conditioners, refrigerators, which use a lot of which are using a conventional cooling, which has various drawbacks, like they are using um, CFCs, HFCs. They are low in Carnot efficiency. Then they make a lot of noise, vibration, so wear and tear is there. So they have limited life. So scientists around the world are working towards creating some sustainable solutions, and for that, people have been working on a phenomena known as a magnetocaloric effect. So on this material, actually in 1996, one Nobel Prize was also given to a scientist when he found out a magnetocaloric effect, which is around at room temperature in a material called as gadolinium. But that also has a issue that this gadolinium is limited to China only. So there are geographical limitations on that. Then few other people came up with some other solutions, like they can use some expensive materials or arsenic based materials. So these have toxicity issues. So what I'm going to advise here is, let's try to find out some solutions which can be used in a low cost manner. And yeah, since I'm working in Singapore, so this is the magnetic cooling technology for a green Singapore. So in short, if a magnetic material is placed and a magnet is brought near to this, then it will show a magnetic phase transition. And because of this magnetic phase transition, it may cool down or it may heat up. When it's cooling down, then we can use this cooling down of the material. We can extract this heat and can be used as a cooling device, whether it can be used in terms of air conditioners or in refrigerators. And comparing to the other devices, these are more efficient, around 50% more efficient than the conventional devices, conventional compressor cooling systems. And they do not have any noise and vibrations. So conventional heat technology is slow, costly, energy inefficient, noisy, requires rare earth metals, a lot of maintenance. So what we are devising is something which is more sustainable, low cost, high energy efficient, and does not require any rare earth metals with geographical limitations. Okay, so you're able to see the screen, right?
Yes, sir, it's visible.
Okay. So here's a small introduction of what is happening during this magnetocaloric effect cycling. So yeah, let me go directly to the materials part, because it will be a material aspect. So just to know here that when a magnet is brought near to a material, then when this magnetic field is applied adiabatically, then the spins will align in particular direction. And once the spins align in particular direction, then the lattice entropy of the system also increases, due to which the heat is expelled. And when this magnetic field is removed adiabatically, that is delta Q is equals to 0, then a cooling phenomena occurs. So at that part where the cooling is occurring, you can use it as a cooling device. So you don't need to go into details of it. It's just application of a magnetic field on a magnetic material. But now the question is, can we use iron as a magnetic material? Can we use iron or any material like cobalt or nickel and make a magnetocaloric device of it? And if a magnetic caloric device can be made out of it, then can we use it straight away as a refrigerator or air conditioner? Then your answer is no, because your material selection is important here, and that's what we are heading towards now. Your material selection and the size of material. So first, the material selection. I think most of you know about the Curie temperature, the temperature at which there is a transition from ferromagnetic to paramagnetic regime. That is called as the Curie temperature. So you need to have a material where the Curie temperature is at your working temperature. Now, what is working temperature? Working temperature means the temperature at which your device should work. For example, if you want to create a refrigerator, then your working temperature is around 10 degrees C, because you want your refrigerator to cool down things to up to 10 degrees C, from 1 degree C to 10 degrees C. So the Curie temperature of your material should be around 10 degrees C. For a wine cooler, it should be around 10 degrees C. But if you want to cool something like data centers and those things, for those big data centers which already emit a large amount of heat in the range of up to 300 degrees C, then you want to cool these data centers to up to 50 degrees C or 30 degrees C is also fine. So that time the selection of material will be different. So based on the application, we are targeting specific materials. Is that clear? Any questions over here? Okay, so I'll go ahead. So in general, we say that when a magnet is brought near to a magnetocaloric material, then we can observe magnetocaloric effect, and this effect can be used uh, to make a device a cooling device. And there are various thermodynamic equations involved. So I won't go into the details of those things. This is just the general background. Yeah, and this is one of the graph which we actually evaluate while creating these devices. So what are the promising applications of these magnetocaloric materials? These can be used in household refrigerators. They can be used in air conditioners. They can be used in electronic gadget cooling. So this is quite a hot topic right now, using magnetic nanomaterials in cooling of electronic gadgets. For example, my laptop, it emits a lot of heat around 50 to 60 to 70 degree based on the usage. But this heat is actually wasted in the environment. Nobody is going to use this heat. So I'll show you later that this magnetocaloric material can be used to make a device which can cool down a laptop. And actually we have cooled down the laptops as well as mobile phones in our lab. So a lot of industrial interest is there. We are working with Panasonic. We have worked with Philips on this. And recently we are working with the Public Utility Board in Singapore for cooling down their data centers using this technology. So this is one of the examples. Then gas liquefaction, this has been already, these materials have been used for this application. Now another one is magnetic hyperthermia. So magnetic hyperthermia means treatment of cancer or cancerous cells using the magnetic nanoparticles. And these magnetic nanoparticles are particularly iron oxide nanoparticles. So these iron oxide nanoparticles are prepared first using various methods that I'll show you later. And then these can be targeted on the specific part of the body where your cancer is developing. And then these particles can kill the cancerous cells without impacting the nearby cells. So currently the main limitation of chemotherapy or such cancer killing therapies is that they may impact the nearby healthy cells also. But magnetic hyperthermia is a technique which will only kill the cancerous cells and not other cells. That is, it is very site specific. Then some applications like heat pumps and heat pumps. Then waste grade heat recovery. Waste grade heat recovery means these you can see these industries. So in these industries, when they are used for particular applications, and then this wastage of heat is actually ejected in the environment, and this heat is used by no one. And the range of this heat is actually around from 150 degrees C to up to 300 degrees C. So within this temperature, a lot of heat is ejected in the environment with no usage. So there is a method using magnetocaloric materials for recovering this waste grade heat that I will show later. And some of these materials have also been used for cryogenic propellants. Now, you might know that for cryogenic propellants, the required temperature will be less than liquid nitrogen, uh, minus 50 degrees C, right? So for that temperature, as I told earlier also, that these magnetic caloric materials will be designed based on the applications. So particular magnetic materials are designed for the cryogenic propellants also. So in this way, we can say that these magnetocaloric materials are used in a variety of applications, promising applications. These are some of the recent industrial interests where the companies are working. As I mentioned earlier, that this is one of the example of GE, which is using this magnetocaloric device for cooling the wine. So this is called as one of the application called as wine cooler. Then there is company in France called as Cooltech. So they have been working on this magnetic refrigeration system from quite a long time. Cambridge is a startup between Cambridge University research students and some more people. BASF also is working towards magnetocaloric materials and creating the sustainable cooling solutions. Now, Hires, they already have created this wine cooler. So this is one of the example, like where the Cooltech is showing the cold drink cabinet here in France in 2016. So this is a little bit outdated one. There are furthermore recent news on this technology. So what I mean to say here is that the magnetic materials, magnetic nanomaterials are specifically used in various applications. Cooling is just one of them. Yeah. So I won't go into details, just like the problem statement. For example, when I started working, the problem statement was, for me, was what is the problem in the existing magnetocaloric materials? What material I can suggest to remove or eradicate those problems? So this is how we create a, we select the material. So when I started working towards my PhD, then my first year was just uh, spent in finding the problem statement and the solution. What can be the solution? So this first year was invested in this one slide only. Then yeah, so when you find out your materials, then you have to tell that what is the significance of those materials and how these materials are better than other materials. Yeah, and then you have to know that how this material is going to work. What is the fundamental science behind them? For example, when I chose my material is iron and aluminum, then I had to study that what will be the effect of chemical doping on it. How will they react inside magnetic field? Because as I mentioned, that magnetic field is brought near the magnetic material, and then what can be the impact of external pressure on it. So these are some things that you have to think on. So once all these fundamentals were made, then I had to go through how to create the material. So here I'm telling you that the material was same. I prepared that material in bulk form. Then in the second part, I created this material, this bulk, towards the micro regime. That is, I created melt spinning micro ribbons out of it, where the size range was in micrometers. Moving on, I created nanoparticles of these materials through a technique called as ball milling. So this is not very conventional technique, because most of the people who prepare nanoparticles is through chemical methods, sol gel methods or hydrothermal methods, and because those are quite straightforward also. But I created those materials by using ball milling because of certain advantages that I'll discuss later. But the logic is, when I selected the material, when I know that these materials can be better choice than the already established materials, then I decided to create all three regimes, that is bulk, micro, as well as nano, and then wanted to study how are the properties different, how are the properties different in different regimes, and whether I am getting better properties in the nano regime or not. If anyone has any question, you can stop me anywhere. Okay, so some of the techniques that I used. So you might be knowing that to study the nanoparticles specifically. Okay, can anyone tell me what is this machine where my cursor is? Anyone online? Any feedback? Ayush, can you hear me?
Yes, sir, you're audible. I'm just trying to identify what it is.
Okay. No worries. If anyone knows any of these machines, actually, I have already put in the names on the left hand side, but just to make it more interactive, let's talk about these, because these are the fundamentals of nanotechnology. Once you know, uh, because nanotechnology means you are studying something which is in the nano regime from 1 to 100 nanometers. Okay, so in that regime, when there is something but it's not visible to our naked eyes, so we have to study those things using some sophisticated techniques. And these are few examples of those sophisticated techniques. If you are going to study nanotechnology, then you will definitely see these machines in due course. So if anyone, any heads up, otherwise I'll just go ahead. Okay, so let me tell you, the first one is called as the X-ray diffractometer. This is a very popular, it's a very popular characterization technique in from which we find out the lattice structure of a material. Since this lattice structure is also within the range of angstrom to nano, so we need to use some sophisticated techniques. And this X-ray diffractometer uses a phenomena called as, anyone knows, Bragg's law. Okay. Similarly, on the second, on the right hand side, you can see this tunnel-like thing, tube-like thing. This is called as a scanning electron microscope. So, a scanning electron microscope is used to identify particles, materials in even smaller range, and they can directly give you a 3D image of that object. Then coming down, this is called as a physical property measurement system, PPMS, that we call it. So PPMS is a very strong and a very powerful technique, because you see from the first one, we are able to identify a material, a nanomaterial. The second one, we can visualize or image the nanomaterial. Then what else? Now we need to find out the properties of those materials, like what is the magnetic behavior of that material, what is the thermodynamic behavior of that material, what are the electrical properties. So once we identify the material, we characterize the material, then we move ahead to study the properties of those materials, if those materials are good for us or not. Correct. So in the third one, when you see here, so with this technique we can easily find out the magnetic response of this material, like what is the Curie temperature, is it ferromagnetic, paramagnetic, something like that. Then whether its resistance is good. For example, if you are going to create solar cells, so you need to find out the resistance of the material. So the resistance of this material can be recorded from this machine. Then if you are studying the thermodynamic properties, then the specific heat of this material, entropy of this material can be studied by using this technique. So this is a very strong characterization tool called as physical property measurement system. I assume there would be one tool in BITS Pilani also like this. Then the last one, it's even more sophisticated, but I won't go through it because it's of yeah. So this is actually electron beam system, and here also we can actually locate what are the different positions of the, where, what are the different location of the atom, where are the atoms sitting, and what are the nearest neighboring atoms. So what I mean to say here is, if you are studying nanomaterials, then you need to know the in and out of the nanomaterial, like how does it look, what are the different nearest neighbors to that material, what are the properties of that material. And once you characterize that material in and out, then you use it for your desired application. It's not like we can directly use a material. Okay. Yeah, so this is one example, like what I characterize through different techniques, like where are the different atoms sitting, and when I change something in my material, then where do the atoms change on. So I won't go through this one. So this just one thing, that when I change from bulk to ribbon, that is from bulk to the micrometer, what is happening. So as I mentioned in the previous slide, that there is X-ray diffractometer. So this is the graph from what we get from X-ray diffractometer. So you clearly see that there is some change in the peak positions. So from these peak positions, we find out how what are the lattice structure of the material. So this is just calculated over here to show you how it's done. Then in the second one, I have done scanning electron microscopy of that. So you see that the bulk material is very plain, nothing over there, planar surface. But when I make ribbons out of it, it becomes something like this, very super cool kind of thing. And this has a drastic impact on the properties. We'll see how are the properties changing. So you see here, so I see a very good enhancement in the properties. So here is this thing. So when I go from bulk to the micro regime, I get a change in the properties. And this RCP is something called as cooling power. So I get an enhancement in the cooling power of that material. Just the materials remains the same, just the processing is changing and the particle size is changing, and we get enhancement in the desired properties. But this is all done through characterizing the material in and out. Then another one, as I mentioned earlier, was when we make from bulk to the milled powder. Milled powder means the nano powder. What is happening? So these are further, yeah, you see in the previous image, we saw something uneven and something like super cool thing. Here we see the particles, but these particles are larger in the size, 100 nanometers. Okay, so when we move ahead, we see that how these particles, okay, let me go forward. How these particles have changed the magnetic properties. Yeah, here. So these particles are actually this particle you can see. So now we move from the micro size to the nano size. How can you see these particles? You see the black ones here. So these are spherical particles, and the size is, you see here the scale bar around 20 nanometers. So up to 20 nanometers of particle size is there. But since we have made it through a physical method, ball milling, so the particle size is not very uniform. There can be a range of particles, and whenever we use this technique of imaging, then we never say that the exact particle size is 20 nanometers. We always say that the average particle size is, or the particle size ranges from what to what. So for my case, I got particle sizes ranging from 5 nanometers to 20 nanometers. So anyone knows what this technique is on the right hand side, image B? Anyone knows what this image is called?
If anyone knows the answer, they can just unmute themselves and speak up, or they may just write in the chat box.
Okay, okay. So people are responding in chat box, is it?
So I'm just asking everyone.
Oh, okay, okay, okay. Yeah. Because I'm not sure if I will just stop the screen, stop this slideshow, then will you be able to see my, I'll be able to see
So
the
I'll
screen.
let you know if there are any queries in the chat box.
Okay, okay, sure. Okay, then let me just check the chat box first. Okay, nothing till now. Okay, so yeah, let's go ahead. So we created these magnetic nanoparticles now, and their ranges was in between 5 to 10 nanometers. So we started from the bulk, created magnetic nanoparticles. And then, as I told, that various applications can be there. So once I chose the material, once I created the nanomaterial out of it, then I had to create a prototype of it. So how did I create a prototype of it? I created magnetic nanofluids out of this. So this is how I created magnetic nanofluids. So I used some chemical methods, some surfactants, stabilize those particles inside some fluid carriers, and then I created. So when you see here on side on image A, this is a magnetic fluid that I created. And when I bring a magnet closer to it, you see the whole of the fluid is attracted as one entity. It's not like the powders are separate and the liquid is separate. So this is called as a stable nanofluid. So this is what we want. So this is one of a big challenge for the people or the researchers working in the direction of magnetic fluidics, because if they want to create a magnetic fluid, nanofluid, then the nanofluid should be very stable. Stable means as a whole it should be attracted to the magnet. It should not be powders and liquid separate. So once I created this, then I created a raw prototype out of it, and then did some COMSOL simulations to see how the cooling is happening. So yeah, just here. I think I have some better presentation for this. Yeah, here. So this is how the magnetic fluidic cooling happens. So this is a prototype of the device where when this is filled in. Yeah, so this is a where the system is at room temperature. You see that the magnetic fluid is filled inside this, and when the magnetic fluid is filled and there is no magnet on the right hand side, so we called the right hand side we called as the heat load, whereas the left hand side we called as the heat sink. Now when we bring in a magnet closer to this is what happens. When a magnet is brought closer to this, the fluid will start moving, and once the fluid starts moving, on the part where there is a heat load, it will lose all of its heat and go to the heat sink, where it will convert again to a ferromagnetic material, whereas in this part it remains paramagnetic. So in this term, if your laptop is a heat load, for example, on this part, your laptop is a heat load, and you just put that laptop on the top of this cooling device, then all the heat from the laptop will be sucked in, your laptop will become cool. Now what's the benefit? Because someone can argue that, oh, there are many cooling devices. The benefit is that this cooling device does not require any electricity input. This cooling device can work forever. It won't require any electricity input. What it requires is just the magnet and a very stable magnetic fluid. So since our lab was one of the first labs which worked on this, so we have got quite 3 or 4 patents on this. Various companies are working with us on this device, and because there are a lot of applications for this, as I told that on this hotter side there can be any heat load, and it will transfer the heat to the cold side, and the heat load can be an industry application, for example, up to 200 degrees C. Then your fluid will change based on the application required. For example, when you cool down a laptop, the fluid should be working temperature for the fluid should be 50 degrees C. When it's mobile, the working temperature should again be 40-50 degrees C. But it's automobile, then it should be around 100 degrees C. Batteries are again 80 degrees C. Compressors even higher. Industries even 200, 300 degrees C. So based on your target applications, your magnetic fluid will change. And there is a challenge how to create this magnetic nanofluid. This magnetic fluid will only be stable when the particle size is as low as possible. And based on few researches, the particle size should be up to 5 nanometers. So what you see, I got up to 5 to 25 nanometers. My magnetic fluid was stable, but not very stable. People are still struggling to get very stable magnetic fluids. Stable means my fluid was able to withstand up to 5 or 6 days. So within 6 days, it will settle down. That means if I put a laptop over my device, then the laptop cooling will take place till 5 days. After 5 days, the device will die. But if my nanoparticle size in that magnetic fluid is up to 5 nanometers, then it will be more stable. For maybe it is stable for around a month or 2 months. Then your laptop cooling will take place for 2 months without any electricity wastage. So this is the beauty of this system. The whole effort goes into researching the magnetic nanofluids which are very stable. Okay.
Observe, why is it that there's a requirement for the small size of the particles?
Okay, because the particles, because there is called as a Brownian motion, right? So if the particles are higher or the particle critical size is more than 5 to 10 nanometers, they will start settling down. Even though you are using some surfactant or stabilizing agent like polyvinyl alcohol or any silicon oil, they won't be stable as soon as magnetic is brought closer to them. If there is no magnet, then then the magnetic fluid will be very stable for quite a long time. As soon as the magnetic is brought near to it, the magnetic force will be higher, and because of the magnetic force higher, it will suck out all the particles from it. But if the particle size is smaller, then it will be more stable inside the material.
Okay, so does it mean that smaller the size of the particle, the faster it can cool down the devices?
Yeah. So okay, the faster cooling down Okay, so there is one more thing here, that this device is called as self-regulating. Self-regulating means the difference between the heat load and heat sink will decide how fast it will cool down. For example, if you are going to cool a compressor which has a higher temperature, then this magnetic fluid will move more faster, and there will be faster cooling of the device. If you want to cool down a laptop, it will be slower cooling down. So this self-regulating means the magnetic fluid will adjust itself based on the temperature difference between the heat load and the heat sink. If you want to cool down it faster, you can put some ice on the colder side. But since we want to make it more lower in the cost, so we just put it normal water over here, and whatever the requirement is on the heat load side. And one more thing, it depends on the magnet also. If your magnet is very strong, then also it will pull the magnetic fluid faster towards its side, and hence the cooling will be higher. So there are various parameters which define like how the cooling will be there. But what you said, that if the particle size is smaller, cooling will be faster. Yeah, because there will be a faster conduction of the material. So if the material is very stable, there will be faster conduction, and hence the faster cooling will be there.
Okay, sir. And also, you just mentioned that it takes around 5 days for the laptop to cool down right now. So,
No,
to
no, no.
make that
I'm
faster,
not saying it takes 5 days. I say that till 5 days it will be able to cool down the laptop. It will cool down in within few minutes. I show you here, for example. Yeah, for example, here just one experiment that I performed. So I was able to get a cooling of up to 5.4 degrees C. And you see here in just 25 minutes, it was able to do a 5.4 degree cooling C. But here I just applied heat load of 2 watt. But I know that the heat coming from the laptop will be higher than this. If it is higher up to 10 watts, then the cooling will be just double. So if I apply a heat load, a heat temperature coming from the laptop is around 10 watt, then the cooling will be 10 degrees C. So within 25 minutes, you will cool down your laptop to up to 10 degrees C. So it's a quite efficient cooling without any wastage of energy. You just need to put your laptop on the device. That's it. And for 5 days, what I mean is that you can cool down your laptop till 5 days. After 5 days, you will see that your laptop is not cooling well. Why? Because the particles have settled down, because the particles are not very stable. But if there is some research in the incoming days, then we can get more stable fluids, then it's much better. For example, our lab is working in developing more stable fluids, and they have more or less developed stable fluids, and they are working towards cooling the data centers. So for example, in Singapore, Facebook has a very big data center. And let me go there. So Facebook has a very big data center. So they have contacted our lab in order to devise something to cool their data centers. So our lab is working on that part. Um,
oh,
okay.
okay. So,
Yeah.
so
Any
like,
other questions?
so wondering. So right now, this is not currently in production, right? So this is still ongoing research area, and
No,
it will
no.
take
This
some
is
time for it to get
currently,
into.
yeah. You see here, one of the example, low grade waste heat recovery using the reverse magnetocaloric effect. IBM wants to cool their own data centers with their own waste heat. What I was mentioning, like the waste heat is going in the environment, and then you can use those. So they are also trying to use these magnetocaloric materials to cool down their data centers. Yeah, this is in, we call it as a prototype stage. So currently it's in prototype stage, because as I told you, the biggest challenge is the magnetic fluidic magneto nanofluid stability. But there is a considerable success in that right now. And the target set by the research magnetocaloric researchers around the world is like by 2030 they will be able to cool down the data centers or the devices using magnetocaloric technology, as well as they will be able to um, I mean, this is just the speculations that every household will be using the magnetocaloric effect based MCE based refrigerators and devices. So this is the speculations, but if they think about 2030, then it may go to 2040. But yeah, it will happen. It will definitely happen because this technology is very sustainable, and at the current need of hour is you need to find out renewable energy sources or sustainable energy sources, green technology sources. This is one of them, and it is very highly researched technology when we talk about the energy sciences or energy based nanotechnological solutions.
Oh, okay, sir. Understood.
Yeah, any other thing, but yeah, this is a good technology. You can google it and then learn more, or you can anytime contact me because my whole research was on this. Yeah, so this is just one slide like what we were able to achieve. So actually, this cooling that I mentioned, 5.4 degrees C cooling, this is quite a significant cooling because we just used a small piece of very small cube of magnet and very low power, 4 watt, and by which we were able to get a significant cooling. So for this one, actually, I was invited to the MRS USA to deliver a talk, and my paper was also invited paper for this event, just because of this very good cooling obtained here. Okay, so moving ahead, since we have 17 more minutes left, so I'll talk about some more functional materials. So this is a domain where we have magnetocaloric materials. Now there are some other uh, applications where these magnetic nanoparticles can be used. So I'll just briefly give you a glance through so that you know that what are the domains where the nanotechnologies are being used. So one example is a high stiffness polymer composite with tunable transparency. Just an example here inside in A, you see here, right? So you see here. So this is something which is very translucent, opaque. You can't see anything. When you heat it up, then it becomes transparent. So this is the logo of Rice University. Then it becomes transparent, and when it cools down, it becomes translucent. So what is happening here? Let's go there. Now you see, so this is one of a very good piece of work that I did with Rice University with Professor Ajayan. So he's a very famous professor of nanotechnologies, and we published this work in a very high impact factor journal of materials today. So what we did here, we took some wax, and inside that wax we synthesized magnetic nanoparticles in our lab, and we put in some logo at the bottom of this, and we heat this material, but there was no contact heating. That means nothing was in contact with it. We heated it in presence of alternating magnetic field. That is, we put this PDMS plus wax inside a coil, and then we started the radio frequency current in it. And once it does it, then the magnetic particles, when these magnetic particles are in nano regime, then they show uh, they show Neil's relaxation. So there is a phenomena in physics called as Neil's relaxation. By this phenomena, they start heating up, and once they start heating up, this wax actually melts down, and once this wax melts down, this logo becomes transparent. And as soon as you turn off the current, the particle starts cooling down, and once it cools down the whole thing, and the wax again becomes opaque. So this is a good phenomena. Why? Because this can be useful, very useful in the security systems. In It can be used by a country's army to create some uh, to prepare some kind of these smart materials. So this is a domain where we call them smart materials. Since the PDMS is itself very high stiffness, so this is a very good solution for, we targeted this application for the security systems. So one of this application is tunable transparency. Another one, this is some more technical, so I will just skip it. Yeah, another one is this. So you see bio-inspired multiple cycle damage sensing and healing in elastomer magnetic nanocomposites. So just to give you idea, what we did here is we created some magnetic nanoparticles, this brown color, dark brown color, and in these magnetic nanoparticles, we mix them inside some fillers. So these fillers are the composite materials. This is some rubber called as NBR. It's a long name. I won't pronounce that. I don't even remember the name. So this is a NBR matrix and then magnetic nanoparticle filler. So this material, this shape is called as a dog bone shape. So when we put this material inside this coil, you see, just now I mentioned, alternating magnetic field or RF coil. When we break down this material, this dog bone shape, we cut it, and once we put it inside this RF coil, it will join, and it will join so perfectly that it is as good as new. But is it possible to do it multiple times? Yeah, we were able to cut it and join it in 4 times in a row. That means it is multiple cycle, and it is multiple cycle damage sensing. And why it is bio inspired? Because the material that we are using here, the NBR, is a biological material. It's a biological rubber, so it's not going to harm your environment at all. So there's a story behind this work. So after we created this called as self healing, because based on this self healing term, this company, Nike. So Nike produces uh, shoes. So their shoes are, they want to make them as as lighter as possible. So I actually, there is a final year project, right? So I had 15 students of final year project under me. So in that group, actually, I gave them a project working on this 3D printed multiple cycle damage sensing elastomer magnetic nano composite work. And I wanted them to work to put this material as a sole of the shoes. So the idea was, if your shoes are broken or they are teared apart or some damage is on them, then you just need to put those shoes inside the RF coil just for once, and they will be as good as new. So after this work, then there was some news regarding this, and then our lab was approached for this, and our professor actually is now working on this project. So Nike and our lab has actually a good collaboration on this work. They are working towards 3D printed damage sensing and self healing shoes based on this work. So this work was published in a very good journal of Wiley. Then one more work. So this is also about magnetic nanoparticles. It is more about control of the biofilm growth. So biofilm is like when the when these bacteria or these contaminants grow up in your environment, then how to kill them? You usually use a various type of sanitizers or these things. But for a bigger setup like the ships, so when there are ships in the water, so those areas of those bigger parts of the ship actually get contaminated with a lot of bacteria over the time. So what we do here, we just created another set of polymer magnetic nanoparticles. So this MnZnFeO4 means manganese, zinc, iron oxide nanoparticles. So these particles are within a particular ratio mixed with the polymer, and then we immerse these particles inside the bacteria. You see, here in the first one, there is a black part. This black part is a magpole. We call is magpole. Magpoles in magnetic polymer composites. So magpole, when these are inserted in the bacteria, then the bacteria will grow on it, because the bacteria loves to come on the magnetic particles. Magnetic particles are biocompatible, so it comes here. And when this is pulled in the electrical AMF, called as alternating magnetic field, the same setup that we have created, so all these bacteria will be killed down within few minutes only. So you see here, in just 20 minutes, the proportion of dead bacteria is more than the live. So this is how we are able to clear off the surfaces by using magnetic nanoparticles. So this is also a very good piece of work which was published in Environmental Science and Technology, using showing the application of magnetic nanoparticles in the field of biology, biomolecules. And then this is also one more good piece of work where you see, then actually once we started working on these magnetic nanoparticles, then we thought that why not work on soft robotics, because it's a very hot topic right now, and nanoparticles are used a lot in these devices. So we did it. So just to show, okay, let me go to my cursor. Yeah, you see here, so this is the magnetic coil that I was talking about, the RF coil. So this is something called as a sheet. So this sheet is of magnetic composite, as 3D printed sheet with a magnetic nanoparticle composite. So when the electric current is on, then I don't know why it's not working. Yeah, Yeah, here, yeah, you see here. So over the time, actually, it opens up like this. So when once it started, it was like this, and automatically it gets open without anything touching on it. So there is nothing touching on it. It's just a coil, and this coil is also very inexpensive. Actually, this coil is found inside your your induction cooker. So people, you might have used induction cookers, right? So on those induction cookers, there is this coil at the bottom. So this coil can be used in, or magnetic nanoparticles can be used, and they will show some actuation. So what we have seen here, just see, let's go here. Yeah, here. So let's see this one. This is the same sheet which is folded, and with magnetic field application, it opens up. Similarly, second one, there is a long wire, something like this, and over the time it winds up. One more example, you see this spider. So this is spider, like this spider web, and over the time, within few seconds, up to 160 seconds, it opens up fully. This is a bird. So you see the wings of the bird are closed, and after the application of magnetic field, the bird wings are opened up. Now, where are the application of these things? These have a lot of applications. One such application is in the drug delivery. If you want to deliver a drug inside your body, but you don't want to spill it anywhere, then you just load the drug inside the packet of this. For example, this image 9.3C. So here, this packet, magnetic nanoparticle packet, and inside this you put the drug and put it in the body. And once you put the body inside this RF magnetic field, it's very easy, it won't harm the body. It will open up and the drug will be released over that part. So this is called as targeted drug delivery. Any questions? If no, let's move ahead. Okay, this is also one piece of work which is in superconductivity side. So I won't go through because this is a lot of physics here, but this paper is actually recently published in Nature Materials, which is one of the highest impact factors in the world, in all the journals. And we did some superconductivity measurements on this. And yeah, then it is also one piece of work which is ongoing right now. We have submitted in a very good journal, Advanced Materials. So here we created magnetic flowers. So you see here at 0 seconds, this is a magnetic flower where there is a Kapton tape, a very simplistic work, very low cost work. Kapton tape is easily available in the market. So on the Kapton tape, I synthesize magnetic nanoparticles and then just pasted over it in presence of some temperature. And when I put it inside the magnetic coil, you see it curls up, it totally winds up. And when I turn off the field, it opens up again. That means it can take the shape you want. Now, how will you decide what shape will be there? It depends on the design that you create. So for that, we do some kind of simulations to find out what kind of design will be perfect. Bottom are the IR images showing up how the actuation is taking place. Similarly, here are the magnetic grippers. So we wanted something to put in, like something is put down and then our grippers come over there, hold it up, go back. So this is one example. So you see here, I have put in one video. Yeah, you see here. Okay, so I'm going to show. Yeah, this is gripping effect of magnetic grippers. Yeah, so this is something like this. You see, this is a gripper that is shown at the bottom. So this gripper comes down. Okay, then it holds up here. So there is just a piece of paper. I'm just trying to show how it holds up that, and it's not touching anything. This white color tape is just a Teflon tape. So now it has grabbed this object, and then it will go just now. Yeah, goes up. So this is just a premature type of example of magnetic grippers. So just to tell you that this work is also very much demanding work nowadays. In case, because there is a technology called as soft robotics. So these magnetic nanoparticles are used widely in soft robotics, and people are appreciating. The researcher community is appreciating a lot. This is called as untethered magnetothermal flexible actuators for soft robotics. Got a lot of applications, miniature robots. So this is a premature work. After this, we have actually created very nice, very beautiful designs of various 3D printed magnetic nano robots of this, and that is ongoing work right now. Yeah.
So,
Okay. Okay.
uh, so,
So, any
um,
questions?
so I was saying that we can just take up any questions if there are, or there's just.
Sorry, I can't hear you. Can you speak louder?
Uh, I'm just saying that if there are any questions, I think we can just take up the questions, or any
Okay,
specific.
okay. I think the time is over now, right? Okay, so these are various applications of uh, magnetic materials. I had a lot of things to cover, so I just like to thank my research group on for this. So currently, I'm not working in the research group, but there are various research papers. These are coming out because I just left the lab around a year ago. So this is also one part of the work where I worked on the structural materials development for aerospace applications, wherein we created some nanoparticles and then used AI and ML um, for this. So just to show you that this is also a very sophisticated technique called as focused ion beam, where a very small carving can be made on on a on a material. You see, we are creating these uh, crest and troughs on the material. So very sophisticated techniques are coming up. Any design you can create over there. The tips are in the nano regime. Yeah, so this is like one of the technique where machine learning can be used to do your nanotechnological research in a faster manner. Okay, so I think, yeah, that's all. And now we can have a open discussion. If anyone had any questions or any questions regarding anything, not only on this topic, if any kind of question you have, we can have a discussion on that. Yeah. Okay, so yeah, the session is open for discussions, any questions, any queries. Just to tell you that currently I am working in Micron Technology, and the CEO of Micron Technology, Sanjay Mehrotra, is also the alumni of BITS Pilani. And yeah, Micron is one of the top semiconductor companies in the world. It is constantly under top 5 companies in the world. I think in the chip production, the memory production, it is number 3 in the world after Samsung and SK Hynix. And for overall semiconductor companies, it's well in top 5 with some competitors being Intel, Samsung, TSMC, SK Hynix, and Micron, and then Texas Instruments and Nvidia, etc., etc. So it's a very good company, and I think the maximum use of nanotechnology is taken up by the semiconductor companies. When I joined in here, then I came to know this because they always try to work in even the lower dimensions, because there is a phenomena called as the tunneling phenomena, electronic tunneling phenomena, that puts on a requirement of even lower sizes. So currently TSMC's Taiwan Semiconductor is working on 3 nanometer devices. So it's very low, means already closer to, atomic size. Atoms is in angstroms, so it's very close to that. So these semiconductor companies work in actually make use of nanotechnologies. Yeah.
Hello, sir. I was wondering if you could give me your take on how Moore's law, how longer is it going to continue? Because people always predict that it's going to stop at some point, but the transistor they still keep scaling down after to lower dimensions. So I was wondering what your opinion is at by which year will this come to an end? And yeah,
I
that's
think in
basically the
terms of
question.
year, we can't really say, because when we talk about these Moore's law, then yeah, there is limitation. Theoretically, there is limitation, but then again, researchers come up with some solutions. For example, this Moore's law has a limitation in terms of planar thing, right? So I'll just give you one example. When there were devices 2 years back, then it is called as a planar memories. So I assume that you might have heard about the NAND memories, NAND, NAND memories. Okay, transistors. So basically, these transistors are planar. Planar means on a plane. But since the Moore's law has limitations, so now people have come up with something called as 3D NAND, means stacking one over the other, one over the other. So this 3D NAND has come up, and from last 3 years it is going on. So this Moore's law limitations has stopped because we already find out an alternative solution of creating 3D NANDs. But then again, question comes up: when is this 3D NAND going to end? So we are facing this problem. Like, I work in the technology development division of Micron, so I constantly come up when there is some high volume manufacturing, like the device that you are seeing in the market today. The fastest memory is from Micron. So this is called as 176 layer memory. So this is already the highest, but the device on which I am working now, it's already more than 210. So we are working on the next nodes, next generation nodes. So for 2 more years, we predict that still we will be able to create these devices. But what after that? So I assume there is a lot of scope in terms of materials, because each material again comes up with the nanotechnology. Each material has different properties. Earlier, the interconnects were made up with copper. Now a lot of research is going on those copper interconnects. For example, this whole semiconductor science is based on silicon. But what if we are able to use graphene as one of the solution for that? Because the electronic conduction on graphene is very, very faster. I don't know the number, but it's exponentially faster than silicon. So as a material scientist, I can say that there is a challenge, there is a limitation based on Moore's law, but the solution will also come up from the material side. So if we are able to constantly find out new materials with improved properties, with the desired properties, we will still be able to beat the Moore's law. And that's what these companies are doing right now. Believe me or not, the maximum research that we are doing in Micron is on material science. That is the nanomaterials, maximum research. I myself work on the dry etch team. So the maximum, the biggest challenge that we have a very narrow dimension, like 10 nanometers. And within this range, we have to etch down the full length. That means our device itself is around 15 micrometers height, and on that height you need to do the etching of the full device at the bottom. And the problem is that the dimension is very small, 10 nanometers. If it touches anything on the sides of the 10 nanometers, the whole device is going to boom, destroyed. So this is one of the biggest challenges right now. Another thing is, when we print the structures on one on another, then there is a technique called as photolithography. So your pattern should be exactly lying on top of that. Since the size is becoming smaller and smaller, there are various issues like defocus issues, spot issues. So this is also one of the challenge, that is our focus spot should be as smaller as possible in the nano dimensions. Then we are polishing those materials, because whenever one step is processed in semicon, then another step comes to polish down everything, make it as perfect as possible. So this is called as CMP. So in the CMP also, again, we face some issues with the small sizes, how to avoid any kind of contaminants, etc., etc. So there are a lot of challenges. Moore's law is true, but there are ways. Scientists will always find out ways. But trust me, when HDDs came up, hard disk drives, there is no future for hard disk drives, because there is no scope where they can do further research on that. They are already working on magnetic materials. Earlier, I worked for some time in the Seagate Technologies in the Ireland. So, Seagate is working on hard disk drives. It's only the one company in the world right now, along with Western Digital for some parts, that is working on hard disk drives. No other company is working on hard disk drives because they are not sustainable. The solution that all the laptops right now contains SSD, solid state drives, right? These are based on NAND memories, whereas hard disk drives are based on magnetic memories, giant magnetoresistance phenomena. So that has already hit the limits. Why the companies is still sustaining is because the big data centers want low cost or inexpensive hard disk drives, and hard disk drives are inexpensive compared